It is section 2.9, dimension and rank. The main reason for selecting a basis for subspace H is that each vector in the subspace can be written in only one way as a linear combination of the basis vectors. This means that each vector in the subspace can be expressed uniquely as a linear combination of the basis vectors. Let's see this example. B, the collection of P vectors, B1 to Bp, is a basis of a subspace H. And if we express a vector in H in two different ways, then the quotients must be the same. That means that the expression is unique. We can easily prove this one. And once we try to subtract the first expression and second expression, then left-hand side, the same x, so it must be 0. And then right side can be written and C1 minus D1, that is coefficients for B1. And then for the second term, there's C2 minus D2, and here B2, and so on, so that the last one will be now CP minus DP and BP, the vector. We can have this one, but here from definition, basis, once you select a basis, then the basis must be linearly independent. These vectors are linearly independent, and linear combination is 0, so that each coefficient must be 0. Okay, this everything over there must be 0, which means that C1 must be D1, and C2 must be D2, and so on. So we proved this one. Okay. Now, for example, if a vector in R3 is expressed as here as a linear combination of the standard basis, so x1, x2, x3 are numbers such that, and x1 indicates that the x is in x1 distance in the first coordinate direction, and x2 is also indicating the x2 distance in second coordinate direction, and so on. Here in this case, x1, x2, x3, this quotient is called the coordinate vector of x. You learned this one, and because we are using the standard basis, there's no special indication depending on the basis. But this vector is called the coordinate vector. We expanded this concept for general basis. Here B, B1 to BP, is a basis for a subspace. And then here x, for each x, the coordinates of x relative to the basis B are weights, the C1 to CP, so that x can be written in this way. Earlier we proved that this expression is unique, so that we may consider the coefficients C1 to CP, collect here. Then this collection is called the coordinate vector of x relative to the basis B, or B coordinate vector of X. Now, for this one, we are using standard basis. So we may say this one is standard coordinate vector. Right? But for that one, we are using general basis. So we indicate here now relative to the basis or B coordinate vector. Okay, so it is a generalization of the standard coordinate vector. Okay, V1, V2 are given here, and X is given, and B is the collection of V1, V2. Then B is a basis for subspace H, which is made spanning V1 and V2. And V1 and V2 are linearly independent. Apparently, the collection of V1, V2 form a basis for H. Determine if X is in H. If it is, find the coordinate vector of B relative to B. Okay, here we have a little bit of a typo. That must be X, and this must be this shape. Okay. Okay, now first we'll see if X is in H. That means that X is a linear combination of V1 and V2. So that first portion, and that is the second portion. For the first portion, now the question is, here is asking if there is some quotients C1 and C2 such that C1 V1 plus C2 V2 must be X here. That's the question, which means that now if we try to write this one in metric form, there's collection of V1 and V2 is a metric, and then here now C1, C2 is X. So we have to see if it has a solution. We may start with the augmented metric. V1 is 3, 6, 2, and that is minus 1, 0, and 1, V2. And right side X is 3, 12, and 7. Okay, this is the augmented metric. Okay, now to avoid the non-integer computation, okay, we will try to subtract this last row from the first one. Then it will become 1, subtraction minus 2, subtraction, that is minus 4. Okay. 1 and minus 2, minus 4. Okay. Now here, and from this one, we subtract twice, then that will be 0. Twice subtraction, there's 2. Twice subtraction, there will be 6. Right? And then, now for the last one, we subtract twice of that adjusted first row. Then that will be 0. And twice subtraction, 4 is added, so it's 5. And then now twice subtraction, 8 is added, so that is 15. Right? And there is 1, 3 with the scaling. Again, this is 1, 3. So these two rules are the same. And we reach it from here, 1, minus 2, and 4, and 0, 1, 3, and 0, 0, 0. Now we have to get, so for the first one, we can easily see from here, it has a solution. That means that here for the first part of the question, we can say it is yes. Okay. Now let's try to find the coordinate vector. Okay. In order to do that, we need to get reduced to echelon form. Okay. Now we eliminated this one by adding twice of the second row, 1, 0, and add that one. Oops, there's minus 4. Okay, so adding twice of that, and that becomes here 2 and 0, 1, 3, and 0, 0, 0. So then now that is the solution, C1, C2. So here, x can be written as C1 is 2 V1 plus 3 V2. That's the expression. And with this basis, this coordinate vector is unique. Okay. Let's see this figure. And V1 and V2 are given, so that twice of V1 and 3 times of V3 will be that 1. So here, if you try to get span of V1 and V2, then these two vector, linear combination of these two vector will make a plane here, the green part of that. Not only this one, and up to this direction infinity, that direction infinity, so that this whole plane will be made. Of course, this x is on the plane. Okay. The grid on the plane in this figure makes H look like R2. It's like a two-dimensional space, but it's not really same as R2. However, we can make a correspondence from x to its coordinate vector. There's one-to-one correspondence between the subspace and R2. And also that preserves linear combinations. And so we call such a correspondence on isomorphism. So we say the subspace in this green, including this green portion, the subspace H is isomorphic to R2. It's not the same as R2, however, looks like, act like R2. Okay? Dimension of a subspace. The dimension of a non-zero subspace H, we'll use the notation DMH, is the number of vectors in any basis for H. That means that once you choose a basis, then if you count the vectors in the basis, then for any other choices of a basis, the number of vectors must be always the same. And here, the number is called the dimension of the subspace. And the dimension of zero subspace is 0. Once there's no non-zero element in the subspace, then we say that is zero subspace, and we define here the dimension of the zero subspace is 0. Okay, here dimension of Rn is n. Quite easy to see that because Rn has the standard basis. Standard basis has n vectors, so that all basis has n vectors. So dimension of Rn must be n. Now, what is dimension of H in this example? Here there are two vectors, and this H is made from these linearly independent vectors. So dimension must be 2. Right? A basis has 2 vectors, so that dimension must be 2. Now, if G is made spanning a vector, then what is the dimension of G? What is it? It can be 0 or 1. If U is 0, spanning set of 0 is 0 subspace, then the dimension of G must be 0. If U is non-zero, then we have only one vector in the basis, so that the dimension must be 1. Okay. Dimension of column space of A, that is, column space, the basis can be decided by PV columns, so that its dimension is the same as the number of PV columns in A. And this one is called the rank of A, so that we are using this notation rank A. That means that dimension of column space of A. Now, dimension of null space of A, and that is now, and when we try to get in earlier section, get the null space, that is the number of vectors in the null space is same as a free variable. From each free variable, we have a vector, so that the null space, the dimension of a null space is same as the number of free variables in A. And that is also the same here, the number of non-pivot columns in A, right? We have the rank theorem. A is an n by n matrix. We will focus on that n. This means that there are n columns. Then here, dimension of column space of A and dimension of null space of A, their addition, okay, we can write in this way: rank of A and nullity of A, dimension of null space of A. Okay, that is, by using nullity, we can express that. So that must be n. The reason is rank, okay, we already see here now, there is a number of PV columns, and nullity is the number of non-PV columns. So we count all the columns, so it must be n. So that is the number of columns in A. That here, null space of A is called the nullity of A. Okay, so, and we are using notation nullity A. Okay. A matrix and its echelon form are given. Find the basis for column space of A and null space of A, and also state the dimension of these subspaces. Let's do that. Okay, matrix is given and it's echelon form. Okay, that is here leading one, leading one, leading one, leading one. In fact, this is the reduced echelon form. There are 4 pivot positions, so that here the corresponding pivot columns, okay, you have to select pivot columns from the original matrix, so that this one, second column, and now fourth column, fifth column, these 4 columns will become a basis because they are linearly independent basis for column space of A. Now, okay, so here, let's say in this way, basis for column space, that is same as, okay, first column and second column and fourth column and fifth column. Okay, and for basis for null space, and we have to solve the problem basically okay, a x equals 0. And from this one, you can get augmented matrix. And then, so here, a and 0. And then you apply elementary row operations. And of course, you reach at that one along with 0 column attached here. Now, so that from this one, we can write in this way, x1 equals same as minus x3. It's a free variable, so free variable must be moved to right side. And x2 is minus x3 again. x3 is a free variable, and x4 must be 0, and x5 also must be 0. Okay, that is x3. Okay, so from here, the solution x1 to x5 can be written along with x3, here a vector. Okay, that is, direction is minus 1, 1, 0, 0. So that this vector is a basis for the null space of a matrix A. Now we can easily say that the dimensions are here, that is 4 for the column space and 1 for the null space. Quite easy, right? We count just the number of PV columns for rank and number of non-PV columns or number of free variables for nullity, right? Okay. Find the basis for the subspace spanned by the given vectors. What is the dimension of the subspace? Okay, a subspace is made by spanning these vectors, and we try to find basis. Now, from these 5 vectors, if okay, they cannot be linearly independent. Now, because it's 5 vectors, in each one is in R4, so the number of vectors is larger than the dimension of the vector, so that it must be linearly dependent. Once you choose out of these 5 some vectors, then it can be linearly independent, so that we can select, we can get basis. Now the method is here elementary row operations, considering these 5 vectors as a matrix, and we apply elementary row operations. Okay, the first row is 1, 2, 0, minus 1, and 3. Now, second row, by adding, we have a 0, by adding minus 1, by adding minus 1, by adding 3, and minus 4, right? And by adding twice of the first row, we have this one 0, and twice, 4 is added, become 3, and same, and that is now, okay, twice added, so minus 2 is added, minus 9, and for that one, 6 is added, which will become 12. Okay, now 3 times subtraction makes it 0, that one, 3 times subtraction, and that is minus 2. 3 times subtraction, because 0 remain unchanged, okay, and 3 times subtraction, so that 3 is added, become 10, and 3 times subtraction, that is minus 9, so that minus 18, right? Okay, yeah, okay, for this one, if you multiply minus 3, minus 3, minus 3, okay, so that one is essentially same as that one. Now, okay, but that is different. Okay, so here we have the first row is not changing, 1, 2, 0, minus 1 and 3. Oops, yeah, I'll rewrite or repair away. Okay. Now that is minus 1 and 3. Okay, we have here. And then, okay, that is 0, minus 1, 3, and minus 4. Okay, we'll move this one after the replacement. It becomes 0 and move to the bottom. And here, the result of elimination of that will be written in this third row. Twice subtraction is 0. Okay, twice subtraction. Now twice subtraction, that will be 4. And then twice subtraction, it'll be 4 again. And here, now twice subtraction, 8 is added, so that minus 10, right? Now this is on echelon form. We have leading one here. Now pivot. There are 3 pivots, and column 1, column 2, column 3, and these are dependent columns, and so that the pivot columns will make a basis, so that here are 3 columns, not from this echelon form, from original one. Here, first, second, third, these vectors will span the subspace, and they are linearly independent, so that these 3 vectors will form a basis for the subspace. Okay. Here we have the basis theorem. Now, for a set of vectors to be a basis, here there are 2 conditions. The vectors must be linearly independent, and also the vectors should span the subspace. Now we start with the p-dimensional subspace of Rn. Then any linearly independent set of exactly p elements in H is automatically a basis for H. Okay. From p-dimensional space, once you choose any p vectors and they are linearly independent, then automatically these vectors will span the subspace so that it becomes a basis. So one of them is satisfied, then the other one will be automatically satisfied. But we have to start with a p-dimensional subspace. So assume we know the dimension of a subspace, then just select any arbitrary p elements from the subspace. If they are linearly independent, then we know that these vectors will span the subspace. So the collection will become a basis for the subspace. Okay, that one is the other side. Any set of a p element of H that spans H is automatically a basis for the subspace H. That means that if you collect p vectors, but the selected vectors span the subspace, then the set of vectors will be linearly independent, so that the collection will become a basis. So one of them, and now for basis, the set must be linearly independent and span the subspace. But one of them is satisfied, then the other one is automatically satisfied. Of course, here the condition is you have to choose always p element, p vectors. After selecting p vectors, if they are linearly independent, then it's basis. Or if these p vectors span the subspace, then again becomes a basis. Okay. Now we expanded the invertible metric theorem. Is a continuation from earlier, the invertible metric theorem. A is on n by n square metric, then the following are equivalent. The columns of A form a basis of Rn, and that means each columns are linearly independent and each column has a pivot. We know in this case it is invertible. And so, and the invertible metric, so the invertible metric, for invertible matrices, the columns will form a basis. Now, the column space must be the Holder space Rn, and so that the dimension must be n. So rank of A is n, the same meaning. Now, here, once it's invertible, then Ax, okay, Ax equals 0. This homogeneous system has only the trivial solution, so that collection of solutions of that equation is just 0. So the null space of A is just simply 0 vector, and so that its dimension, nullity, must be 0, right? Okay. Okay, let's see this example. If the rank of 9 by n matrix, so that is the number of columns, right, is 7. Rank is 7 means that there are 7 pivot positions. So if you consider Ax equals 0, then there must be one free variable. What is the dimension of a solution space of Ax equals 0? So it is asking the dimension of the null space of A. It's the same as the number of free variables or the number of non-pivot columns. That must be 1. Already it is saying that there are 7 pivot columns. Out of 8, the remainder one is only 1, right? If A is a 4 by 3 matrix, so we have now 3 columns for the matrix, and the mapping is 1-to-1. 1-to-1 means that every column has a pivot position. So the rank of the matrix is 3. Now, what is the nullity? Dimension of null space A? The rank and nullity summation must be same as the number of columns. In this case, 3. But already the rank of 3, so the nullity must be 0. Right? Quite simple. Now we have here true or false problems. Each line in Rn is a one-dimensional subspace of Rn. Is it true? It is false. To be a subspace, the first condition is including having the 0 vector. Once the line is not passing through the origin, then 0 is not in the set, so it cannot be a subspace. So once you consider true statement, then okay, you can change it to be true. Each line in Rn passing through the origin is a one-dimensional subspace, then it is true. But just arbitrary line not passing the origin cannot be a subspace of Rn. The dimension of column space of A is the number of pivot columns of A. Is it true? Yeah, it's true. Right? Already we know that. The dimension of column space A and null space of A add up to the number of columns of A. Yeah, that's true. It is the rank theorem. Now, a basis, P vectors, is a basis for a subspace H of Rn. Then the correspondence x to the coordinate vector makes H look and act the same as Rp. Is it true? Yeah, it is true. That is, remark over there. We consider that it's not really same as Rp, but looks like Rp and acts like Rp. Okay. The dimension of null space A, that is nullity, is the number of variables in the equation Ax equals 0. Is it true? It's false, right? The number of variables is now n, but to make it true, you have to put over there free variables. The number of free variables, then that is the nullity, the dimension of null space of A. Okay? Okay, that's the end of the section. Thank you.